Hello, welcome to this pre-recorded lecture in the quality control course. We are going to today discuss a little bit about analysis of variance, which is a second step in our hypothesis testing lectures, which we started then last week with looking at t-test and f-test in the context of deciding on equal or non-equal variances. So for analysis of variance lecture, we are going to first talk a little bit about multiple comparisons. Then we look how for one factor cases we can conduct an analysis of variance. And then choosing in if we have a one factor or multi-factor analysis of variations. And we will also consider how to, after analysis of variance, to narrow down which groups are statistically significantly differing from other groups that are considered. But before we go into the mathematics, let's a little bit look at a case study. So in drug design, researchers are doing screening of large virtual libraries. This is basically a long list of molecules that are suspected to be potential drugs. And for such drug candidates, different properties can be calculated. And these properties are then further tested statistically against thresholds which are required for a drug to have. And later these molecules which are promising are being synthesized, and then they are going through various different testings, first with cells, then with test organisms, and then finally in the clinical trials. And it is unfortunate, but a really large proportion, about 90% of the drugs are failing in the later stages, which means that in the first stages, there are many drugs which are passing to the later stages, though they are actually not potent. Or actually, a bigger problem is that though they are potent, they are having side effects which drugs should not have. And one of the reasons that is being discussed as the source of this is that in each of these stages, when we are considering very many drug candidates, we are doing statistical comparison of a control group and the group where the drug has been administered for all of these drug candidates. And this means that we are doing multiple comparisons. This leads to a small but significant bias, and even the magnitude of this bias increases the more of those multiple comparisons we are doing. And the same effect is also associated, what we are going to remediate today, is also associated with so-called p-hacking, which means that researchers, be that wherever in academia or in industry, are compiling research studies so that they would have a large set of comparisons which are statistically made. And it happens that when we do very many of those comparisons, there happens to be an increased probability of rejecting null hypothesis when it actually should be still stayed with. And for example, one fun example of where very many comparisons have been investigated. So this is basically trying to associate different rather random events with each other, which means that basically a long list of historic data has been taken, and each rather independent event has been statistically compared with another event. And the result is that it was found that people killed by venomous spider attacks is correlated with the letters in winning word of Scripps National Spelling Bee, which are completely independent of each other and cannot actually be associated. But this rather strange outcome, which also falls under the category of bee hacking, comes from the fact that there were just very many comparisons which were statistically made, and most, if not any, of those comparisons were not first logically hypothesized to occur, meaning that just because we did many comparisons, some of these happen to randomly hold, but it does not mean that they truly hold. This comes basically from the type 1 error that we are allowing in our hypothesis testing always. Because as we remember, in a default setting where we are not having very dramatic cases for consequences for type 1 or type 2 error, we were saying that we allow ourselves to reject null hypothesis in 5% of the cases when it actually does not hold. So what does this multiple comparisons then more numerically mean? Let's look at that a little bit. Firstly, when we are doing t-test, which we looked last week, then we are comparing two samples, and we allow a preset percentage of type 1 errors. So this is what we set with alpha with the significance level. So when we chose 5%, it means that if we do a test basically 100 times for the same question, then in 5% of the cases, we would reject null hypothesis, even if it actually holds. But what now happens if we are want to compare, not just do just one comparison, but we want to do two comparisons. So maybe let's look at our extraction recovery example. So we had the Soxhlet extraction and ultrasonic extraction comparison, but maybe we come to an idea, maybe just a normal solid liquid extraction would also work for extracting the pesticides from soil. Maybe we don't even need to really give energy in terms of heat in Soxhlet or in terms of ultrasound in the second extraction. Maybe we just do the liquid solid extraction. Well, in this case, we could think, let's go to the lab and do the Soxhlet and ultrasound extraction. Let's do also the solid liquid extraction, and then compare both the ultrasound extraction and the solid liquid extraction with the Soxhlet extraction, which is the current default method. And then this would mean that we would need to do now basically two comparisons. We would need to do the default, the current status, which is the Soxhlet extraction, with the ultrasound. We need to also compare Soxhlet with the solid liquid extraction. Now, if we did just one comparison, just the Soxhlet ultrasound, we allowed ourselves to reject the null hypothesis in 5% on 5 days out of 100 if it actually held. But now let's assume that we are going to the lab and doing the extraction, or again on 100 days, but we do all three, and in all days we are doing two comparisons. So that would mean that with our type 1 error or significance level that we were allowing, we are making a wrong decision. So we are rejecting null hypothesis on 5 days, and on 95 we are doing it correct. However, now on these 95 days where we stayed with the null hypothesis, we are also doing a second comparison. the comparison between the Soxhlet extraction and the solid liquid extraction. And if we are allowing the same type 1 error, same significance level, 0.05, we have another 5% chance in these 95 days or during these 95 days to make the type 1 error. That means actually that on 4.75 days out of the 95, we are rejecting the null hypothesis for the Soxhlet solid liquid extraction comparison, even if they actually have a statistically insignificantly different means. So this means that actually only on about 90 days, if all of the extractions are giving the same recovery, only on 90 days out of 100, we are in both comparisons staying with the null hypothesis, which here then would be the correct decision. That means that on 10% of the cases, a little bit less than 10 days, or 10 days if we round to full days, we would be rejecting either one, for one comparison or the other, the null hypothesis, which means that actually our type 1 error across multiple comparisons is not anymore quite the same. Actually, it's much higher. And when we do this mathematics for several comparisons, here comparisons are on the left-hand side, and the probability of rejecting the null hypothesis for one or say multiple of the comparisons that we are doing when they are actually holding the null hypothesis is on the right-hand column. And we see that, yes, for one, if we allow alpha 0.05, it is 5%, but if we do two, it's already 10%. And if we happen to do 5, it is about 1/4, so 1/4 of the cases we are rejecting at least one null hypothesis which actually holds. And if we now put it into the context of drug design, where we might be having thousands, if not hundreds of thousands of virtually screened or also experimentally screened drugs, then this explains why we are passing too many drugs to the next stage if we for each drug are doing a separate test for comparing it with a no-administered drug or a placebo. Okay, so what can we do against the errors arising from multiple comparisons? Well, we do still want to often enough compare multiple different samples arising from different distributions, e.g. different extraction processes with each other. And t-test, due to the error in multiple comparisons, does not really suit this if there are more than two samples involved. And therefore, to go into comparing more than two, so 3, 4, 5 samples with each other, we need to look into one-way or multi-way analysis of variance. And here, as the examples, we are looking at cases where the samples come from groups which we have very specifically designed. So it's called so-called fixed effects model. That means that, for example, if we investigate the temperature, then we are saying that or assuming that the temperature is something that is under control, and maybe we are testing then temperature 50 degrees, 100 degrees, 150 degrees or more levels. So let's start looking how analysis of variance works. And before we look at the math again, we need to halt for a bit to look at the terminology. And the important term that we are using in this lecture, which we haven't had before, at least not to such an extent, is a factor. And factor is something that is very essential in analysis of variance, but it will come also back to us in the design of experiment later on in the program. And this is something which usually is an experimental condition that we can alter, but we can also keep it at a specific level. And in terms of analysis of variance, it happens to be the parameter, basically, which impact we are going to investigate. So, for example, the factors can be temperature, pH, wavelength. And they become factors if they are of interest for us from our statistical testing or from our chemistry experiments point of view. If they are just always kept constant, they are still parameters of our method, but they won't come into our statistical tests with, for example, in analysis of variance. And in terms of comparing or analyzing the effects arising from these factors, we also have factor levels. That means the specific numerical values, or not always necessarily numerical, but specific values of these factors that we are investigating. So, for example, if we are investigating temperature and in one set of experiments, it's maybe set to 300, and pH is set to 2.1 units, while it may be in a different experiment, a different sample, we are doing measurements at 200 degrees, and pH is 5. So then the levels 300 degrees and 200 degrees are factor levels for temperature, and for pH, it's 2 and 5. Now, we can have different types of analysis of variance, and we start with one-way ANOVA. That basically means that we are one factor with number of different levels which we are investigating. For example, if we are having a liquid-liquid extraction, we know that the extraction recovery from water to an organic phase, let that be octanol or hexane or whatnot, depends on the pH for ionizable chemicals. That means acids or bases. And therefore, we might be interested in testing different pHs. But we keep everything else constant. We keep the volumes in the extraction constant. We keep the organic solvent constant. Everything else is constant. But we vary the pH. And we can, for example, test pH 3, pH 4, pH 5, pH 6. And do in each of them carry out a number of replicate measurements, ending up with 4 samples, where our factor is the pH, and the factor levels are then 3, 4, 5, and 6. So 4 levels. And if we would be doing now multiple comparisons with t-test, which is the not suggested way to go, then we would need to compare the extraction results from 3 pH obtained at pH 3 with results from 4, 5, and 6. And results at 4, we would need to additionally compare with 5 and 6, and results on 5 with also 6, ending up together with 6 comparisons. But in analysis of variance, we can first actually ask a little bit different question. We can ask if there are any effects, and then start looking at specific levels and which of them are causing the effects to the extraction. So for doing and answering this question, we need to build up a little bit on a mathematical model. And here the assumption is, and this usually holds as well, that all of the experimental results on different factor levels are coming from the same distribution, where we on each factor level. So for example, from our extraction on each of the 4 pHs, have done a number of replicate measurements here shown with here shown and marked with the number n. And on each of these rows here is shown the results for one of the factor levels. So here, for example, from the previous case would be pH 3, pH 4, pH 5, and pH 6. And we have K different levels. And this number can be really, really different depending on what is the research question that we are analyzing. Now, each of these individual analysis results will be impacted by the random errors arising from simply replicating the measurements, but also by the impact of this factor level. And that means that we can try to break this individual experimental results down into different components. So the replicated measurement J for the factor level I can be expressed as the mean from this specific sample, so measurements on this specific factor level I, and the random error. This is very similar to any replicated measurements coming from one distribution. So that means basically that any of those y values over here is explainable as the mean in the same row plus the random errors affecting the measurements for this specific case. And this is exactly what we assumed also in t-test and what we were also saying in normal distribution case. So the mean is what we would get if we would, is a point estimate, of course. And if we would do infinite number of measurement, it would approach then the true mean, assuming no systematic effects. And each individual outcome is then impacted by the random effect. So this is for each of the specific rows, and so each of the factor levels. Now, however, we also want to investigate the different rows relative to each other. So the extraction outcomes depending on the pH, so the factor levels that we changed. And here the assumption is that the effect on each of the factor levels is explainable by a general mean of the experimental results. So a mean experimental results across all measurements that we have done, plus the impact of the factor level. So that we can think of like this, that if we would be just doing the measurements in all those 4 pHs, then the total mean, if we don't consider the pH at all, would here be this mu. But in each pH, there is a specific impact on the extraction arising from the pH, which is a systematic effect, a not random effect. And this is explainable then by this alpha over here. So we have a general mean across all the measurements that we have. But in each of the levels, the measurement mean is impacted by a specific effect of these factor levels, the alpha. And furthermore, individual measurements are impacted by the random error. So basically, this boils down to the same idea that we have. We have the impact of the factor levels and we have our random errors. And the impact of the factor levels is then a systematic compound arising from the purposefully changing the factor level. Okay. Now, before we can actually do the test, we also need to think about what are the assumptions of the test that we are going to make. And here we need to make 3 assumptions. The first one is that all of the random errors are independent. This basically means that all of the replicates that we are considering, all values here, all of those y values are independently measured. Of course, the same row is affected by the same pH, but it is an independent replicate. That means that the random aspects that were varying from experiment to experiment are the same. It does not work, for example, if the random effects for all of the first replicates across all the pHs are the same. This is something we shouldn't do, because then we are violating the randomness, the independence of the random errors. Secondly, we are assuming that the mean of the random errors is 0, which usually holds, but important is also that the variance is unaffected by the factor level. This in practice in chemistry means that the repeatability on each of the levels is insignificantly different from the other levels. So the repeatability stays basically the same, independent of if we are testing pH 3, pH 4, pH 5, or pH 6. And in many cases, this holds. In some cases, this does not necessarily hold, especially when we are going into cases where we are having stability problems, or we are already going very close to noise, for example, when we are considering peak areas as our inputs and so on. So this is also something we should think about. Can we reasonably assume that the repeatability on each of the rows, each of the factor levels of the parameter that we are considering is actually the same? And last but not least, we assume that on each of the samples, each of the rows, or each of the factor levels, the random errors follow the normal distribution. So basically, we assume that the replicate measurements are following a normal distribution. So when we have verified that all of those hypotheses or these assumptions actually hold for our case, then we can write down the hypothesis. And this is similar to what we had in case of t-test, that we go in with assuming that there are no effects. So we assume that on all of the factor levels, the effects don't exist, so the individual means are equal. So we assume that the mean extraction recovery at pH 3, pH 4, pH 5, and pH 6 is the same. This is our default assumption, so our null hypothesis as well. And we can write it either as that the means for each of the factor levels of the investigated parameter are equal to each other, or that the alphas here, so the effects, are equal to 0. That would mean the same hypothesis. And the alternative hypothesis would be that there are at least 2 levels, so at least one comparison where there is a statistically significant difference. That means that there is at least one factor level which is substantially different statistically from the other levels. So one of the means is so much different from the other means that it cannot be explained by a random chance alone. However, pay attention that the alternative hypothesis does not tell us which one of the factor levels it is, only that there exists one that is different from the others. Which one it is, we'll need to find out later. And this makes sense. We first ask, is there any? And then we can ask, which one it is. So now when we have the assumptions in place, we can actually start doing the testing. And basically, what the analysis of variance is asking is that, is the variability in each of those measurement results that we have got explainable by effect of the factor level? And is this effect that we can assign to the factor level statistically significantly larger than the random errors? So basically, we want to compare the alphas here, so the effects of the factor levels, with the random errors. And this is a sort of logical because our question is, are the differences in the means of the samples larger than what can happen just by random chance alone? And the difference here is compared to t-test that now we don't ask between us two specific means of two samples, but we ask across different factor levels. And that will change the test a little bit. So we don't compare the means, but we compare the alphas for each of the factor levels as one aspect with the random errors across also all samples that we have measured as the second aspect. How do we do that? Well, we consider the alphas as one source of variability in the individual outcomes of the tests and the random errors as the other source of variability. And why I'm using the word variability is that we will consider them as the sources of variance in the data, and we will have a comparison of variance arising from the factor levels and variance arising from the random errors. So how do we do this mathematically? Is that we first need to know how many data points we have. This is basically how many measurements across all of the factor levels we have done. We need to also, for each of the factor level, calculate the mean. So this is a point estimate here of the mean. So this is here similar to the mu I, where the mu I indicates the true mean for a specific factor level, while in reality we have a limited number of measurements and we don't get access to the true mean, but we have a point estimate of the mean. So that's why we are denoting it with the Y and a floor on top. So for each sample, we calculate the mean. So basically, when we go to our experimental results table, we calculate one mean for the first factor level. So here it was pH 3 for us. We calculate another mean for the results from pH 4, another mean from pH 5, and another one from pH 6. And then this gives us access to the point estimates of the mu I here. We also need to calculate the overall mean, which is then the mean across all of the results that we have got. So that would be the mean of all of these results that you see in here. And this will give us access to the point estimate of the mu, so point estimate of the extraction across all the pHs that have been tested. That, of course, also means that we have access for the individual effects of the factor levels, so the alpha values over here. And we also actually have access to the random errors because the mu i's that we calculated as the point estimates of the mean on each of the factor level and the individual outcomes give us also access on to the random errors. And what we will be doing is that we will be estimating the variance from the random errors. So the variance that is explained by random variation, and the variance that can be associated with changes in the factor levels. How do we do that exactly? Is described in this analysis of variance table, where we basically divide up the sum variance in all of the results. So here is it's shown as the sum of squares. So this is not yet corrected for the number of measurements that have been done. So the sum of squares is explainable as the individual measurement result minus the total point estimate of the mean. So across all measurements done on all factor levels. So this is the total variance of all the measurements. But we divide this up into the alpha term, so the impact of the change in the factor level, which is here up in the first row. So basically we have the point estimate for the sample mean on each of the factor levels. So that's the indicated by the subscript i's, and the point estimate across all. So this difference here gives us the alpha I. So it gives us the impact or the change in the result caused by this specific factor level I. And when we also know how many factor levels we tested, so K, in case of the extraction with different pHs, it was 4. Then we can compute from the sum of squares also the variance as the ratio of the sum of squares divided by the degrees of freedom here. And the degrees of freedom here is the factor level -1, because when we are fixing or calculating the total mean, we are reducing the number of degrees of freedom here by 1. So this first row, it tells us until here what is the variance arising from changing the factor level. But we also need to compare it with the variance that is just coming from random errors. So just repeating the measurements at slightly varying different environmental conditions. And for this, we can evaluate variance on each of those factor levels separately. So we evaluate variance here, 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 as the source of random errors, so as the source here. And then we are summing them up also across all of the levels. So in the table, when we look at here, then each individual measurement result is impacted by a random error relative, causing the difference of this outcome relative to its mean. So the mean on this factor level. So when we have 3 replicates done on pH 3, then they all are explainable by the mean on this factor level and the random error. So when we subtract from the individual measurement result, the mean on this factor level, then this gives us access to the random variance arising from repeating the measurements. And we do it first inside one factor level, and then we sum also overall of the factor levels. So we get a random variance estimation from all of the measurements that have been done. And when we take into account also the degrees of freedom, so here it is the total number of measurements, so n, minus the number of means that we are calculating to evaluate the random variance, so that is here k. Then we can also get access to the variance, random variance estimate from the repeating the measurements. And now when we have the 2 variances here, we can analyze this as with the F-test, because F-test is applicable when we want to compare 2 variances. And here we compare the variance coming from the factor levels, which we are assuming to be larger in case there is an impact on at least one of the factor level in comparison to the others. And we compare it then with the variance arising from random errors only. And then you can use this to evaluate if the factor levels actually have an impact. And here we can again do comparing the F that we calculate from the 2 variances with the critical values. Here it has 2 degrees of freedom. We have to account for the degrees of freedom in the variance arising from changing the factor levels and the degrees of freedom in the random errors part, as well as we need to account for what is our significant level, so type 1 error that we are allowing ourselves. And this depending on this, if the variance in the caused by the factor levels is larger than what the test suggests, then we are accepting the alternative hypothesis, so saying that there is at least one factor level which is causing significantly different results from the other levels. Or if it is smaller, that means that probably the differences in the means for the different samples are explainable by the random variation alone, and we should stay with the null hypothesis. And here on this, in this critical F value, the alpha indicates the significant levels, not to be mistaken by the alpha as the effect of the factor level in the mathematical formulation behind the analysis of variance. Neat. Good. Let us look a little bit on the examples as well. And here we have an example where one is carrying out derivatization, so that is chemical modifications through reactivity to conduct fluorescence analysis. And that is because very many analytes do not fluorescent on their own, but they can be made fluorescent through a chemical reaction. However, sometimes the products of the derivatization are not extremely stable, so they are formed with relatively high recoveries, but they degrade again depending on the environmental conditions. And here we have a case where the a derivatizing reagent called OPA is used to determine spermidine with liquid chromatography. And the question now is, how should the sample be analyzed, kept before the analysis with the liquid chromatography and coupled to a fluorescence detector? And the question is, does the derivatization really need to be done immediately? Can it be stored for up to an hour in the dark conditions? Can it be stored 1 hour in a dark vial? So these are these brownish vials that you can keep LC samples and GC samples as well in. So it's not really completely dark, but it is a darkened glass. And last option is maybe we can use it, wait for 1 hour just under normal conditions. Just keep it in a transparent glass vial in the outer sampler or on the benchtop. And for this, the measurements as peak areas have been measured and recorded here in a table for each of these 3 conditions marked as A, B, C. So the different rows. We have 3 replicates. And then the peak areas are given here, which have been also normalized over all of the measurements so that the mean would be 100. Now, when we do analysis of variance, our null hypothesis is there one of the factor levels? So here, one of the conditions that is giving, So our null hypothesis is that all of the storage conditions are giving equal peak areas independent of which of the storage we are using. So there is no difference which is statistically significant. Every variation in this table can be explained by the random variation alone. While our alternative hypothesis is that there is at least one level, so either A, B, C, or D, which is significantly different from at least one other level, so that this difference is substantial and cannot be explained by random variation alone. Our significant level, how to choose this one? Well, we need to think what is then the what is then the type 1 error. Here it would mean that we are saying that we are deciding that one of the storage conditions has a substantially different impact on the peak areas, while it actually does not. And here it would basically lead to somewhat more thorough analysis of what is actually impacting the peak areas. And it can be argued, but probably it is not the most dramatic or most awful outcomes that can happen. So maybe staking with the 5% or alpha 0.05 as a significance level could make sense. Good. So then we can go on when we have our hypothesis and our significance levels decided, and we can actually perform the analysis. And performing in R or any command line program is actually rather straightforward and also reproducible, meaning that if my data set, which basically is this table over here, a little bit formatted, in this case, I would basically actually consolidate it into two columns so that I would have one column which tells me the condition and the other column which tells me the values, while in or below the column heading, I would have altogether 12 rows. The first one saying condition A, peak area, normalized peak area 102. That second row would also be A, then telling me that it is the second replicate had a value 100, and then the third row saying it was 101, and then 3 rows for the condition B, 3 rows for condition C, and 3 rows for condition D. This is just to make it more easily machine readable. And if I have this, I can do the analysis of variance test here, where I'm saying that the peak area is what is my investigated property, or and I'm investigating in the context of the storage condition. So here, just the condition is my column heading. And I'm also asking for a detailed output, which gives us a little bit more information. And what I would be getting in my R output looks something like this. And it's super simple because there's only one comparison that I'm doing. So it's only telling me if the condition is a variance arising in the data in the peak areas from the condition is larger than what is expected by random chance alone. And therefore it tells me it investigated the impact of condition. It does tell me the total sum of squares. It does tell me also the sum of squares from the replicates, and it also gives me the degrees of freedom for all of those. Then it also gives me the calculated F value. So what is the ratio of the variances arising from the factor level and from the random errors? And from the decision perspective, it also gives us a p-value. So basically, what is the probability that the variance that we are observing for the factor levels, arising from the factor levels, is explainable with the random variance. And we see here that this probability is 4 times 10 in minus 4, which is significantly smaller than our significance level 0.05. And as a default, also 0.05 is here shown as a usual significance level. And we also see that here this is deemed as significant with a star here. And last but not least, we have also here a G's value, which is basically indicating us how strong this impact is. And in case of one condition, it's not really very informative, but when we would be testing different factors, so not only the storage condition, but maybe we would also test the time as different factor levels, then this could give us a little bit more insight on comparing these two with each other. And we can, so basically here the conclusion is that the p-value is lower than our significance level, which means that we need to reject the null hypothesis and accept the alternative hypothesis, indicating that at least one of the measurement conditions is showing substantially different results. So in terms of peak area from the other conditions. And now to get a little bit more maybe visual results to this statistical value, we can also make a box plot here where each of the dark lines here shows the median results for this specific storage condition. Here with only 3 replicates, the box plot is not so informative, but if we would have more measurements, it becomes more and more indicative, as with all visualization. Theoretically, or what is here also visible, is that the box covers 50% of the values. And you understand in case of 3, it's not so much. So this is called the lower quartile, meaning that 25% of the values are lower than the starting of the box. 25 are also higher than the end of the box. So this is quartile 25, and this is quartile 75, or also called upper and lower quartile. The whisks over here show us what are usually drawn until the lowest value or the highest value, depends on if it's the lower risk or higher risk of the data that are displayed, unless the lowest and highest value are further away from the box than 1.5 times the width of this box. Then we would have the result indicated as a dot somewhere here or somewhere below, and this can be treated as an indication of potentially having outlier values. However, what we can use these box plots here is to get a little bit visual point of how the conditions are impacting. And we do see that with the immediate analysis and with the dark analysis, the boxes are largely overlapping, which indicates that there is maybe very little impact on from immediate analysis to storing for 1 hour in the dark. But we do start seeing that the boxes for the dark vial condition versus holding it really in the dark, maybe in a cupboard, is different. So boxes don't even overlap anymore. Actually, the whisks also don't overlap. So this might be a substantially different condition. And also the keeping the sample in transparent vial is not having any overlap with the dark vial, nor with the cupboard, nor with the immediate analysis. So it can give us a little bit of a first hint which levels of the storage conditions can be showing substantially different results from the others. However, this box plot is more a visual helping understanding tool, but it doesn't necessarily tell us statistically at what levels are different and how much. And for looking at this, we need to go one step further and start investigating the levels more detail.
So after we have figured out if we have a factor level that is statistically significantly different from the other levels with the aid of one-way analysis of variance, we might also ask ourselves which level it then is, which is different from at least one more uh, other level. And to answer this question, we can use post-hoc tests, which in different ways try to now I'll give us an indication of the differences in the specific levels. Um, Before we start doing the post-hoc tests themselves, we need to compute something which we are assigning as the experimental variance. So actually this basically the same experimental variance that we were considering in the analysis of variance. So we calculate again the sum of squares from the individual factor levels, where these are the repeated measurements on the specific factor level, and this one here is the mean on this factor level. And by taking into account how many replications have been made and how many factor levels there are, we can calculate the experimental variance estimates, the MS squared here. And this we will use then as a basis of how large difference in the levels, in the means of the two levels can occur just by random chance. And the first way to now look into the specific level differences is by Fisher's LSD test, which basically actually considers the T critical value, taking into account the degrees of freedom. So that means how many replications were made, but also how many means were calculated. So the N, large capitalized N, is the number of measurements across all factor levels, and K is the factor levels as a reminder. The MS square corrected with the number of measurements on levels of I and J that we are comparing gives us then the estimate of the experimental variance for the difference in the means of these two factor levels that we are comparing. And with this LSD, we can account, then we can compare this to the individual differences from all levels on this one factor that we are studying. And here, the logic is that if we already know that there is one level that is different, then we can now start looking into which one it is, but we don't really do any specific adjustments in the significance level based on the number of comparisons that we are making. The number of comparisons is only used in the degrees of freedom of the T statistics, so the N minus K in here in the Fisher LSD test. Therefore, Fisher LSD test is rather optimistic in finding factor levels that are different from other levels. Almost on the other end of this scale of being critical is Bonferroni correction, which looks almost the same as the Fisher LSD test. But here, the significance level is also divided by G here, which indicates how many comparisons will be done. And this then means that if we are doing only one comparison, we have a significance level of 0.05. But if we are doing two comparisons, then we are now already wanting that after two comparisons, the significance levels is 0.05. So that only after two comparisons we can have a type error probability of 5%. That means, of course, that the more comparisons we make, the larger the t-value gets. And that means that harder and harder it is to find differences in the factor levels. So that's also actually one of the reasons why it can be that if one applies Bonferroni test later as a post-hoc test, then first analysis of variance says that one of the factor levels is statistically significantly different from others. But after doing Ponferroni test, it might be that after taking the correction into account, there isn't any level that is deemed statistically significantly different. So this is one of the most critical post-hoc tests, and this is also what we are going to largely use in this course. There is also a possibility to make use of other statistics besides t statistic. For overview, there is a Tukey test, which takes into account how large a range of the mean values across levels. So the Q here is observed and then compares individual pairs taking this into account. Or there is a Schiffer test, which takes as a starting point the linear combination of the means. So the y1, y2, and so on here are the means on the individual factor levels. And it tests the linear combination of these factor levels, where C1, C2, and so on are coefficients in this linear combination. And with this, it is basically observing one variance caused by the factor levels in comparison to the experimental variance, and then makes use of the F distribution again. There are also other methods and other corrections that one can apply, but let's look now a little bit how this is applied. So basically, when we do either a Fisher or Bonferroni correction, then after analysis of variance, which told us the factor levels actually do have an impact, then we would follow up with a t-test here. We would still have the peak area as the measure of sensitivity in this example, and it depends on the conditions. We didn't have paired results, and we do want a detailed output, but we also need to now add that we want to adjust the p-values. And just a heads up here a little bit, even though it looks like we can do the t-test, we should technically do the t-test here only after the analysis of variance. So always analysis of variance first, and then doing a t-test with the correction for the p-value, so a post-hoc test. And here we use a Ponferroni correction. And here we had, for this case, several different conditions. So we had six comparisons altogether. And what we see here is that on the first column, we see the difference in the mean peak areas of the two conditions that we are comparing. Then we see the individual mean estimates for both groups. Then we see what was the Y. Then we see what groups they are. We see what were the number of measurements. We see here the T statistics. We also see the p-values and the degrees of freedom. They are not integer numbers, but doubles, because in case of unequal variances and equal variances, we had to, in case of t-test, where we didn't know if the variance is equal or not, we needed to first test for this. And depending on the outcome, the degrees of freedom would also change, depending on how we needed to make the correction. Then we also get the confidence level lower bound and confidence interval lower bound and higher bound for the estimate of the mean of the differences in the means. We see what sort of test it is. Is it one way or is it one-sided or two-sided? And now comes the p-adjusted. So the p-value here in the middle did not take into account that we are making altogether 6 comparisons. But the p-adjusted here in the pre-last column does do this, and you automatically see that the p-values are much larger. And this is because the t-criticals are being changed. And you also see now that we can find which ones are statistically significant. And here we will see that only keeping the sample for 1 hour in dark and keeping it in completely in the dark, and keeping the sample in a transparent vial is different. So row number 2, the last row as well, immediate analysis without any storage time versus keeping the vial in the transparent, the sample in the transparent vial are statistically significantly different. And now when we go back to the box plot that we had before, we see actually that we were hypothesizing here that maybe the dark vial conditions and the transparent vial conditions could also be different because the boxes don't overlap. But because we're doing so many comparisons, we need to be more critical in the p-values, and actually what looks significant in the box plot is not here deemed statistically significant after accounting that we want to keep our total significant level at 0.05.
Okay, so we have looked into the analysis of variance for one factor with multiple levels, and we have also looked how later to figure out which of the factor levels is significant from which other factor level with the multiple testing and correcting the p-value for multiple testing. But actually, often we have more than one factor or more than one parameter that is affecting our experimental results. For example, extraction recovery. And therefore, we need to also consider a two-way analysis of variance. And that means that we have to consider that we don't have only one factor at different levels, but we have effects of different factors. We need to therefore modify what we were writing down as a mathematical model in the one-way analysis of variance, where we had the measurement result of each individual measurement result depending on the mean across all the factor level values, plus the effect of this specific level on which the measurements were made, plus the random error. But if we have multiple factor levels that we are considering, then we need to consider that the one level can have an impact, the second level can have an impact or an effect, and actually also the two levels can have a co-effect, or also called interaction. This would mean, for example, when pH has on extraction recovery one effect, temperature has another, but when we combine both, then the effects are not anymore the linear sums of the effect of the pH and the effect of the temperature. What does this mean, or how this can be? Well, I like to bring here usually an example from real life. So if you have ever been into doing some sports, then you know that you can basically train either speed or duration. And you can think of this in the training, for example, running, that one of the effects could be the factor level of the duration in which you are using in your training, while the other effect could be then the speed or the pace of your running. And of course, both of them would have a specific effect, usually when you are training for a longer period of time and until reasonable limits, your performance will improve. Also, when you are running within your personal reasonable limits quicker or with a higher pace, then you will also improve. But what does happen is that if one tries to simultaneously train for longer and with a higher pace, then in one point, this will not anymore yield a performance improvement. Actually, it will more yield injuries and decrease in performance due to extreme exhaustion, meaning that we have an interaction between how long we train and what pace we are training with. And similarly to this examples from sports, the same happens in chemistry. For example, if you're optimizing a chromatographic method and you are considering mobile phase composition, you're considering pH, and you're considering the organic modifier content, then both of them will have impact your retention factors that you might be optimizing. But they also will co-interact because, as we were saying in the ASM course a few lectures back, then the organic modifier content in the mobile phase will impact the pKa and the pH. So even if we tune the pH and organic modifier content separately, they will interact with each other. And this is this gamma term here that we will also need to bring to picture if we are having two factors, factor A and factor B, with its own different levels. But these different levels can also interact. Importantly, we are not necessarily limited with two factors with A and B. We can have actually many factors and also consider combinations of them if we have the data available for that. So in this case, our null hypothesis and alternative hypothesis need to be written for each of the impacts or effects that we are studying or testing. So we can test for the effect of the factor A, factor B, and also the combination of A and B. Therefore, we will also write 3 pairs of hypotheses for each of these both factors and their interaction. So for factor A, we would write very, very similarly as what we did in one-way analysis of variance, where we're saying that the null hypothesis means that none of the factor levels has a effect on the analysis, which is not explainable by random variance alone. In case of and then the alternative hypothesis would mean that at least one of the levels has a significant impact that cannot be explained by random variations alone. The same holds then for B and also for the interactions here for the A and B. And however, we have to keep in mind that the number of interactions is the multiplication of the factor levels A and factor levels B. So if we have 2 levels for both, or then we would have 4 interactions that we are considering. If we would have A measured on 3 levels and B on 3 levels, then it would mean that we have 9 interactions to consider. So each possible combination of the factor A and factor B levels. Now, when we go into mathematically testing these effects for different levels, then we need to calculate again different means. We need to calculate for each level of the factor A, their mean, ignoring completely the factor B. So we don't consider that it would exist at all in this mean calculation. So we average over all levels of B. We also need to calculate the means for each of the factor level as in B, ignoring A. So we averaged over all 8 levels here. And we also need to calculate now the means which account for both the levels in A and B. So these are then the ones for the interaction terms of A and B. So this would be the mean of the case where the factor A is at level I and the factor B is at level J. And this would then mean that if we have A, small a denoting as the number of levels for A and small b denoting the number of levels for B, then we would all together calculate A times B means like this. So three conditions in A, or 3 levels for A and 3 levels for B, would mean 9 possible interactions and also 9 means describing these interactions. And we also need to calculate general mean. This is what is our baseline. So if neither of the factor levels nor the interactions are significant, then all of the individual measurement results will be explainable by this general mean plus the random errors in the measurements. Now, based on these, we can also calculate the variances. And these variances we will calculate by accounting for how many values actually contributed to this calculations of the specific means that we are going into. So effects of A, very similar again to one way ANOVA, are the basically here the alpha squared and summed together. Where the mean is then from a specific level of factor A and then compared to the general mean. And the same for the B. And for the interactions, it's a little bit more complicated because this is the mean on a specific level. And we need to compare it to the means when we ignore the combination of A and B. So the mean in A and mean in B. And we compensate for the fact that they do two subtractions here by adding the central mean here. From these, we calculate the variances for the alpha term, the beta term, and then the gamma term. So the impacts or effects of A, B, and then the interactions of A and P. And we also need to calculate the variance from the random errors, which means that we take the individual values and the means on this combination of the factor levels to estimate the experimental variability that is purely arising from the repeatability and cannot be coming from the changes in the factor levels. Then these variances are imputed into 3 different F-tests that we are carrying. So we can do an F-test to test if factor A has an impact. So we compare the variance arising from changes in the level of factor A with the variance coming from the experimental repeatability, so random errors only. And we can do the same for B, and we can also do the same for the combinations. And this means that actually in multiple factor analysis of variance, we are doing multiple testing already inside this analysis of variance. But unfortunately, this is how it is, and we don't really have an alternative way to look at it either. The decision making from that is the same as usual, that we are comparing our p-values with the significance levels that we are assigning. And let's look now at the small case study where we have a development of a liquid chromatography method for detection of imazalil, the pesticide that is widely used in fruits and vegetables, especially citric ones. And we are using mass spectrometric detection. We use 2 columns and both have been tested on the high pH and on the low pH. And the gradient is a rather generic one from 5% to 100% of acetonitrile, 15 minutes, isocratic elution to elute the late eluting compounds in the end. And lastly, the percentage is brought down to the starting acetonitrile content and the column is stabilized. And you were repeating the measurements and in both columns and with both pH. And you do want to know if either a pH or the column has an impact. So is there an effect on the measurement results? And you also have are considering that maybe there is a little bit of an interaction between the pH and the column because one of those columns is a mixed mode column, which in addition to the very standard reversed phase stationary phase also has a little bit of ionic interactions available, which means that pH could also have here a little bit different impact than it does in C18. So first, maybe to look visually on these results, it is from the peak areas are recorded here, and on the x-axis you have pH, and it's again a box plot stacked in the way that for one pH we can draw different boxes for the two different columns, for the mixed mode column and for the reversed phase column. And we can little bit so we can see from this box plot, we can see that at pH 2.7, both of the columns are giving right. There are the low peak areas, while for the higher ones, they are giving for the higher pH, the peak areas are also higher. So we might now want to see if this is also statistically significant. Can we expect that the column or the pH has an impact? Then to do this, we can run basically very similar code as what we did in case of one-way analysis of variance. But now when we are starting with our data set containing all the peak areas and factor A and B levels, we can say that we want to do an analysis of variance. We are testing sensitivity, expressed here actually only as a peak area. And here we say compare to which or on which. And pH and column are what we are considering. And if we are interested or if we are hypothesizing that the interactions should also be considered, we can use the multiplication sign here between. If we know from chemical logic that the interactions cannot happen, we should write the plus sign, which means that we want to test for the impact or effect from factor A and effect from factor B, but not for the interaction of these two. And what we would get here in response as a result would be that we have three effects here: the effect of pH, effect of column, and the combined effect. We get here the different sums of squares, indicated also the degrees of freedom for all, the F values from comparing the variances for each of the effects with the random error variance. And here are the P values here. And now we can compare the P values with our significance levels. And if we usually in chemical analysis when we are often staying with the 0.05, then here we would be assigning the effect on the pH primarily. And this is the only one that is statistically significant. So for pH, we need to reject the null hypothesis and say that the alternative hypothesis is what we are accepting here. And now when we have multiple comparisons, this G's value can also become useful because it indicates us which one is numerically having the sort of largest impact. And well, here actually only one of them is statistically significant. So it doesn't make much sense to look into this, but if multiple would be statistically significant and we would need to draw conclusions, which one to optimize further, would prefer to go for the ones which has the largest magnitude impact. So the G's value would need to be higher here. And here we can also make a comparison of the levels later by using multiple comparisons. However, here the multiple comparisons really does not happen because we have only two levels for the pH, which means that if we do a Ponferroni correction, our p-value and adjusted p-value are actually the same because we are still having just two samples which are going to be compared. But if we would have more, then again, the correction for the multiple comparisons makes sense.